In the last video, we discussed naming so-called carboxylic acid salts. Those are the conjugate base that results from deprotonating a carboxylic acid. In this video, we're going to look more closely at exactly how acidic are carboxylic acids relative to other functional groups we've talked about, and how can we evaluate based on the structure of a particular carboxylic acid how acidic it will be relative to other carboxylic acid molecules. So let's take a closer look. We can compare the acidity of carboxylic acids relative to other types of functional groups that we have learned about by taking a look at their relative pKa values. And what I'm going to do here is list some typical pKa values. These can be manipulated somewhat by bringing in other functional groups in the vicinity of these types of groups. But just to give you a general layout of the relative acidities of different carboxylic acids, we'll start from the left here with the least acidic, and we'll move toward the right toward compounds that are increasingly more acidic. And we're focusing here specifically on organic molecules and functional groups that we have came across at one point or another along the way. So we'll start with the very low acidity end of the spectrum, which was our alkanes. Alkanes, molecules that have sp3 carbon atoms with no heteroatoms. So for example, ethane would have a typical pKa value for an alkane of approximately 60, meaning that this molecule is not easily deprotonated at all. It wants to hang on to those protons like crazy, and the reason it wants to hang on to those protons like crazy is a loss of a proton would create a very unstable conjugate base product. As we go along the chain here, we're going to go from alkanes, which are very non-acidic and hence very reluctant to lose a proton, to molecules at the other end of the spectrum, the carboxylic acids, which are called acids because they are the most acidic or among the most acidic of the functional groups that we will come across within organic molecules. And as a result, carboxylic acids have a pKa of around 5 or so is their typical pKa value, indicating a huge difference in the propensity of a carboxylic acid to lose this proton that's directly bonded to the oxygen versus an alkane, where the fact that the carboxylic acid has a much lower pKa value indicates that this proton is readily lost. And by readily losing that proton, what that implies is that the product of that reaction must be relatively stable compared to the product we would create by losing a proton from an alkane. In the middle of this spectrum, between alkanes at the very less acidic end and carboxylic acids at the very much more acidic end, we have things that are more in the middle, such as alkynes with their sp hybridized carbon. The sp hybridized carbon of an alkyne makes the proton or protons that are directly bonded to that sp carbon much more amenable to losing a proton and creating a relatively stabilized product, giving a pKa value of around 25, indicating that when an alkyne loses a proton from here, the conjugate base product that will have a negative charge on this sp carbon is much more stable than putting the negative charge on the conjugate base of the alkane, which would require having a negative charge on this carbon that I'm highlighting here in the alkane molecule. We can then go onward toward even more acidic molecules in this progression, going to things like alcohols. An alcohol, I'll put in R as just whatever alkyl group is there, OH, will generally have a pKa value of somewhere around 15 or so as the ballpark for that. So not nearly as acidic as a carboxylic acid, so it's not nearly as readily capable of losing this proton, but much more capable of losing a proton than an alkyne or an alkane, due to the fact that when we lose a proton from an alcohol, that would place a negative formal charge on an oxygen atom, which is much more electronegative and therefore better able to handle that negative charge than placing the negative charge on a carbon atom. So then delineating between the alcohol and the carboxylic acid, we could ask the question of why is the carboxylic acid more acidic? In other words, why does it have a lower pKa than an alcohol? Because in both cases, when we react with a base to lose a proton from an alcohol or a carboxylic acid, in both cases, we're going to end up with an oxygen that has a negative formal charge. So, for example, if we have our alcohol molecule here, like so, we react it with a base. We'll say sodium hydroxide, which is Na plus OH minus. To give an equilibrium in that reaction, what's going to happen is that the oxygen anion comes over, grabs the proton from the alcohol acid, that forces the oxygen-hydrogen bond to break, and the electrons go on to the oxygen, giving us our alkoxide anion, and as well, our sodium cation. So this would be a sodium alkoxide as the cation-anion pair. And then additionally, water would also result from that reaction as, in this case, the conjugate acid product. Similarly, when we do this process for our carboxylic acid, we also will deprotonate the hydroxy group by bringing in the lone pair electrons from the sodium hydroxide, like I'm drawing out the sodium hydroxide here. So those lone pair electrons come over from the sodium hydroxide, grab a proton from the carboxylic acid, forcing the oxygen-hydrogen bond to break, and giving us our carboxylate anion with our negative formal charge right here. We would also have the sodium cation there in this carboxylic acid salt, because we have a deprotonated carboxylic acid now with our cation. And our conjugate acid product here, again, like in the top case, would be water. And so really the difference between these two, when we analyze which of these two reactions is going to be more favorable, we can deduce that this bottom reaction has to be the more favorable reaction, meaning the reaction where the equilibrium is further toward the product side, further toward the right in this equation, because we know from up top that the carboxylic acid has the lower pKa value. So why is it the case that this reaction's equilibrium lies further toward the side of the product? Well, we have to look at the stability of the product in each case, because the more stable the product, the further that equilibrium is going to lie toward the right-hand side, meaning that the starting material was more acidic, hence more reactive, yielding a stable product. And the reason why the carboxylic acid deprotonated salt product is more stable is because of resonance. So there's a second resonance structure here that I'm showing in black, where that second resonance structure we can draw to show that the negative charge on the oxygen is shared, delocalized in other words, over two different oxygen atoms, like so. Hence, sharing the burden of that negative formal charge over two different atoms and therefore stabilizing the conjugate base product here that I'm highlighting relative to the alkoxide product of deprotonating an alcohol, where the oxygen, single oxygen atom, is just stuck with the entire burden of that negative formal charge. There's no resonance to delocalize it. So resonance delocalization of the negative formal charge across two oxygen atoms is what is going to result in a carboxylic acid being dramatically more acidic than an alcohol molecule. So this is really a direct demonstration of the power of resonance in altering the properties of a molecule, because by bringing in that opportunity for resonance to stabilize the product, we create a molecule, a carboxylic acid, that has a much lower pKa value than an alcohol molecule. So one way that we can conclude what we were just looking at and I just erased was we can say that when we are looking at acids and the acid strength, we can say that the stronger the acid, meaning the lower the pKa value of that particular acid, the more stable the conjugate base product will be. So in other words, to compare the acidities of different possible acids, we need look no further than the conjugate base of each of those acids. And the more stable that conjugate base product, the stronger the acid that led to that particular product. And so what's going to stabilize the deprotonated conjugate base product? The conjugate base product is an anion. It has a negative formal charge on the oxygen atom in the case of those deprotonated carboxylic acids. And so how do we stabilize an anion? The way that we stabilize an anion is by having groups that are electron withdrawing by resonance or induction. So we have groups that are electron withdrawing by resonance, generally being the most important factor, followed by, if there's no way to use resonance to stabilize the negative formal charge by moving it around and sharing it over different atoms, then we look to induction. And for induction to stabilize that anion, induction also needs to have an electron withdrawing effect. And for induction to have an electron withdrawing effect, that's generally going to mean that there are electronegative atoms such as halogens nearby. So let's do an example here of comparing a couple of different carboxylic acid groups to evaluate which is going to have the lower pKa value. So in this example, we'll go ahead and look at trifluoroacetic acid. So trifluoroacetic acid has a CF3 group here. It's a common biological reagent used in a bunch of different molecular biology applications, such as for precipitating proteins. And we'll compare that to acetic acid, which would have a CH3 group right here. So we want to ask which has the lower pKa value. In other words, which of these two molecules is more strongly acidic? So taking a look at these and trying to determine which is more strongly acidic, what we can do is evaluate the stability of the conjugate base products that would result from losing a proton from each of those. So I'm going to put minus H plus to indicate that each of these is going to lose a proton by reacting with a base. So losing a proton here and here would give us our conjugate base products, which would be like so. For the trifluoroacetic acid deprotonation, would give us a negative charge on the oxygen here. And if we come over to the deprotonated acetic acid, our acetate anion would have a negative charge right here. Now we look at resonance and induction to determine which of these will have a lower pK value. We're asking which of these two products is more stable. Whichever one is more stable is going to be the more favorable product, the product where the equilibrium will lie further toward that side of the product, meaning that the acid starting structure was more acidic, it had a lower pKa value, it was more prone to reacting and having the equilibrium lie further toward the side of the product. So which of these two is more stable? All right. So looking at these, in order to stabilize an anion, we need an electron withdrawing group by resonance or induction. By resonance, these two are identical because in both cases, the negative charge can be shared over the two oxygen atoms of the carbonyl group. There's no distinction between these in terms of resonance. There's no way to draw a resonance structure where you can take any of the lone pair electrons from the fluorine and bring those over. That is just not going to work. There's not a way to accomplish that. And so then, since resonance is identical, we look at induction. Keeping in mind specifically, we need electron withdrawing groups because there's too much electron density associated with this part of the molecule where the oxygen atoms are sharing that negative formal charge. So we need something that's going to pull electron density away from that region of excess electron density. So we need an electron withdrawing group. And by induction, we see that the left-hand molecule, the trifluoro, is superior to the methyl group because the fluorine is an electronegative atom. And since we have 3 fluorines, that's going to be very strongly electron withdrawing. So our fluorines are strongly electron withdrawing by induction in these molecules. And so those are going to stabilize our conjugate base of our trifluoroacetic acid, or TFA for short, for trifluoroacetic acid. So this is our conjugate base of trifluoroacetic acid right here. That one is the more stable of the 2 conjugate base products. And so the more stable of the 2 conjugate base products will correspond back to the more acidic of the 2 starting materials, or in other words, the one that has the lower pKa value. So let's do one additional example here. In this example, we're going to look at which has the lower pKa value, and that is, does para-hydroxy benzoic acid or para-nitrobenzoic acid have the lower pKa value. So in each of these cases, what I'm going to do is write out the conjugate base product that would result from deprotonating each of these. If we deprotonate para-hydroxybenzoic acid, the COOH group has the most acidic proton, so it's going to go from being COOH to being COO-. At the para position, we would still have that hydroxy group, as in para-hydroxybenzoic acid is the name. Versus, we compare that to our benzoic acid, para-nitrobenzoic acid to be specific. We deprotonate that, so it's going to lose its proton at the COH. At the para position, we still have our nitro group, so I'll plug in my NO2. And then we ask which of these is the more stable conjugate base product. Because whichever of these conjugate bases is more stable is going to correspond to the starting structure that was more acidic, because the more acidic the starting material, meaning our carboxylic acids here, the more stable the product that will result from deprotonating that. And so taking a look at these, we have to think about the fact that electron withdrawing groups are going to stabilize the anion. Electron donating groups are going to destabilize the anion, because the anion at its heart has too much electron density. It needs to get rid of some of that electron density in order to become more stable. And so that's why electron withdrawing groups are going to stabilize the anion. They can be electron withdrawing by resonance or by induction. Now, back in chapter 17, we looked at a variety of different so-called directing groups as ortho-para-directors or meta-directors in electrophilic aromatic substitution reactions, and those trends were based on whether overall particular substituents on aromatic rings were electron donating or electron withdrawing, where our electron withdrawing groups acted as meta-directors, our electron donating groups acted as ortho-para-directors. And so we can also apply that type of information here, our understanding of electron donating versus electron withdrawing groups, recognizing that NO2 in our chapter 17 materials, and still here, was an electron withdrawing group. It was a very strong electron withdrawing group. It was a very strong meta-director, in other words, because of the fact that it was electron withdrawing. The hydroxy group, on the other hand, was one of our stronger electron donating groups. And so as a consequence of this, keeping in mind that the hydroxy group wants to donate electrons toward the rest of the molecule, the nitro group wants to withdraw them and pull them away from the rest of the molecule. Since the rest of the molecule has an excess of electron density due to this negative formal charge here, having the electron withdrawing nitro group is going to help stabilize the molecule. And so, as a result, The more stable of these two structures, these two conjugate bases, is going to be the one on the left. The more stable conjugate base product always links back to the stronger acid. And so therefore, our stronger acid of these two is going to be the para-nitrobenzoic acid. In other words, the para-nitrobenzoic acid is going to be the one that has the lower pKa, because lower pKa equates always to the stronger acid. So with the information from this particular video, you should now be comfortable with looking at two different carboxylic acid groups and assessing which of those is going to have the lower pKa value. In other words, if those are both present in a container and they react to the base, which one is going to lose its proton in reacting with that base?